All right. So today, in today's flipped classroom, we're going to cover 4 questions, and these 4 questions are asked by everyone in the class here. And so essentially, the questions are on when how do we look at servicing interrupts? The top half versus the bottom half. So when an interrupt occurs, how do we make sure that we service it efficiently without blocking other tasks? But also get that work done, even though the work might take a long time. And we don't want to put the stuff all in the interrupt handler. The related question to servicing interrupts is that, okay, when we get an interrupt, what is the actual execution flow for servicing that interrupt? So we went over that, last time, but we'll go over it again in terms of, interrupt comes into the system, and then what happens? How does the system actually first detect that, hey, there is an interrupt triggered, and two, what kind of interrupt is it? And then how does it actually inform the CPU that after it executes the current task, that it should go and service the interrupt? So that's on the interrupt execution flow. Then there is questions on the Watchdog timer, and why do we need like a special kind of timer? Why can't we just have like an interrupt that that actually knows that the system is stuck? Um, and the last question is, okay, well, if we have very infrequent kind of events, say like once a year, once in 10 years, should we still use interrupts? Okay, so so let's get started with that. So we'll first start with servicing these interrupts, because we didn't cover that last time. And so what that means is that suppose let's look at an example, right? So you have a keyboard, and essentially whenever you type something on the keyboard, you have some shortcuts, right? So whenever the keyboard key is pressed, then that keyboard key basically triggers an interrupt service routine and says, hey, the keyboard was triggered and this key was actually pressed, right? So the interrupt service routine is able to capture that I pressed key B, and then it can say, okay, well, if this person has pressed key B and say like the control and key B, and that key pair is like a shortcut to saying launch the browser, right? B for browser, and it's going to launch the browser. But the problem with that is that once I want to launch the browser and I launch the browser, or start some app over here, if this is I press key B over here, and that triggers the keyboard interrupts the processor, and the processor finishes whatever the current instruction it was doing, and then it jumps to the keyboard interrupt service routine. And that interrupt service routine over here is saying, okay, well, let's first grab the character that caused this interrupt, and then it has a big switch case statement over here. It says, okay, what's the character? If the character is B, then let's start the app, and this app in our case is the browser. And if you have like say 20 tabs or 100 tabs open on your browser, it'll take about 5 to 10 seconds to load your whole browser. And but if 5 to 10 seconds are running, and that's just basically waiting for this app, for this browser to launch over here, the keyboard interrupt service routine can't just be blocked for that amount of time. You want to be able to do other work. You want to be able to refresh your screen, get other interrupts like that, right? Network packets are coming in, and if you block all network packets, then the browser won't load. And so then what do you do, right? Um, so the problem here is that I want to just register, look, key B was pressed. And then if I also put in now do this work and then exit out of the keyboard interrupt service routine, doing this heavy duty lifting work over here, less time consuming work, and blocking this interrupt service routine from any other key press, and blocking any other interrupts from happening, because we are disabling interrupts till we finish the current interrupt, then that's going to cause a lot of problem, right? So what kind of problem will it cause? It's a very obvious question, but what do you guys think? What kind of problem will me getting stuck in this cause actually? Anybody. Don't wait for someone else. Life's too short.
I mean, if the interrupt gets stuck in another function, it's just blocking the whole system from running essentially.
Yeah, but what would get blocked, right? What are all the things that are running on a system getting blocked?
All the normal threads, right?
So give me some examples, right? What would get blocked that now nothing else is going to work, right? So but what are normal threads, like even what's running on your laptop on a regular basis? What are the interrupts that are getting triggered continuously on your laptop?
What are hardware interrupts?
Yeah, but specifically what kind of hardware?
Is there some output compare interrupts? Because you're servicing this keyboard interrupt, so I can't do like any like timing output compare and stuff.
Sure, but let's say from your laptop, right? You're all on your laptops. We are on this Zoom call. What kind of interrupts are happening during this Zoom call?
Like taking internet packages and stuff.
Packages, okay, you mean packets. So
Yeah.
getting internet packets, definitely. What else? What are the other interrupts happening? So those packets will basically come in, they get buffered into your network card, and that's essentially from your Wi-Fi, and say the network card can buffer like at the most like four packets. And then after that, it basically just starts dropping the packets, right? So now while we are launching this app, and you're also running like say Netflix on the other side, or you're watching Zoom on this side, then all these packets start to get dropped, and it says, wait, till we launch this, we're not going to be able to do anything else with that, right? So what other interrupts are happening while we are here?
Your mouse?
Yeah, the mouse is moving. For at least for me, the mouse moves often. Y'all have some of y'all might have just this Zoom in the background and just be like looking at Reddit or something like that, right? Or Facebook. See, I see a couple of smiles there. It's fine. It's fine. Uh, so, uh, so you want other applications to run, but also the like, what are we doing? We have the microphone on. The microphone is constantly interrupting the processor, right? The microphone is saying, okay, well, here's another packet. Here's another packet. So all of these interfaces inside the processor, it is constantly getting interrupted because it is running its own services, right? It's running its tasks. The kernel is interrupting the tasks to switch to the next task, to the next task, and so on. So what is an obvious way in which we could sort of say, let me just register this B and then somewhere else call this app? How would we do that?
Oh, I'm sorry. Very, very quick question. So getting stuck in the keyboard ISR, would that mean that the computer would basically not do, the processor would basically not do anything at all until, I guess, forever?
Yeah, so basically getting stuck in an interrupt, at least in our world with the microcontrollers, that we can only service one interrupt at a time, right? So if while we are servicing that one interrupt, we disable all other interrupts from being serviced. So you're right. You can only, in this case, we're only servicing one interrupt. On your laptop processor, you can have an interrupt, and if there is a higher priority interrupt, that can actually interrupt that interrupt and start running. So suppose I'm starting this app over here that was connected by this keyboard press. We'll look at an example of that, right? So while I'm servicing an interrupt, I can have another interrupt, but so that's a nested interrupt. We can't do that in our microcontroller, but in a processor, you can have an interrupt during another interrupt. And there would be a limit to that, right? So you can't have like this nesting happen infinitely, but that would mean that once the interrupting interrupt actually finishes, then it goes back to the previous interrupt and finishes that one. So, but in our microcontroller, we can only service one interrupt at a time. So it is disabling global interrupts from happening while we are servicing this interrupt over here.
Gotcha.
So the question is, I just want to get B and I want to do this kind of work later on. How can I do that?
Maybe you could store it in a global buffer or something.
I could store this in a global buffer. I could keep this, I could have a pointer to this function over here. And so I can have some kind of thing that the interrupt here basically just says, put everything in this buffer, that these characters, and then go and process them afterwards. What it means by afterwards is just register what the interrupt was, what was the character, capture that, and then later on later on interpret and execute what that character means and what kind of work needs to be done with that, right? So here we are just capturing this super fast. We're getting out of we just register one character over here and we get out of the interrupt service routine. And then later on, when the processor schedules, this application, which is essentially just processing the buffer now. It says, okay, let's look at what characters we caught so far. And then it's saying, oh, we got a B. And says, okay, let's process B. And B basically means let's go and call this. And then we interpret that part, right? So we're putting that in some application code, which is, say that is in a task that is just saying servicing the interrupt, after the servicing the keyboard characters, right? So, and there we are just taking one character at a time and servicing them. So when do you see this some kind of a lag, right? So many times when I start my MacBook, while the screen is just coming on, and I quickly type in my password because your password is almost like muscle memory, right? So then none of the dots show up over there, and then you wait for like 3-4 seconds, and suddenly all the dots show up at the same time, and then the screen gets unlocked. So that little delay that you see there, that is the delay that the interrupts were registered and the characters were captured, but they haven't been able to service it. And what is servicing, the keyboard mean is that we're actually going to read the characters. First, we're going to display them on the screen, and then we're going to sort of execute the command. Okay, well, we're displaying, say password character 1, character 2, character 17, or characters till the last character. And then we hit enter, and then it executes the enter character after that. And but this is done as a separate task, right? That is not part of the interrupt service routine. So now that sounds great, right? What we did was we decoupled the interrupt, like what is the signal coming in from the interrupt and what is the content of that interrupt, from actually, processing the command that character, signifies, or that is related to that, right? So suppose now, so I basically get out of the interrupt service routine, and later on, in the main program or in a separate task, I basically can just process, the input buffer over there, right? So what kind of, so now as I'm processing this input buffer, what kind of problems can occur? Question for you guys. It's a flipped classroom, guys. You got to be teaching me now. Someone who hasn't spoken yet, don't wait for someone else to speak. It's a small group, so have no fear. So the question again is, okay, look, we are servicing this interrupt. We've got it. And now we are actually going and executing this task over here. What kind of problems can occur here?
Be an issue if like another interrupt happened while you were executing it?
Yeah, so that's right over here, right? What happens like if while we are processing this command and we haven't removed that command yet, another interrupt comes in and adds to that queue. So this is like the example where we have this buffer over here, that we had the linked list in the beginning of these slides, and the linked list basically, while it was getting updated, it got interrupted, and then another element came in, and that caused a big mess up, right? So the way this actually happens is that we have a top half, which is basically saying, let's just process the interrupt and put, the work to be done in a function, and we call that function later on. And so different operating systems have, very structured ways to process interrupts very quickly, and then to put that work, in these functions. And so like these functions are like, they have like in Linux, for example, they're called tasklets or soft IR queues or work queues. And essentially they're saying, okay, well, whatever work you have, put that in the bottom half, which is basically a queue, a structure that is there that's saying, okay, we have an interrupt. We basically add to this queue and says, okay, well, this is the, you need to call this handler whenever we process this event. So the keyboard will say, okay, here's a character, call the process, call this process command function whenever you can, but I'm done. I'm handing it off to you now. And so it's saying, okay, well, now it's your problem, but I'm going to go back and, close up the interrupt so the processor can continue running. Okay, so let's look at an example where we have some concurrency problems, right? So say we have, we are basically printing out the time, right? And the time is running on an interrupt. And now and so that's one task, right? We want to print out the time. Another thing is that we are actually typing on the keyboard. And as we are typing on the keyboard, I type THIS space is, and then while, and so basically capturing the character is being put in the interrupt service routine. And that's saying, okay, well, I'm capturing the characters, and then I'm saying, okay, well, I'm putting all of this in output buffer, and that buffer will just, whenever print string is called, then we will start printing out the characters. So print string is basically just going through the string that I have, like this is a line, and it is just sending a character now one by one to the screen. It's just putting THIS space IS, and it's just running. It's just a simple function that is printing a string to the screen. And then there is an interrupt service routine for whenever the clock basically is 2 o'clock, 2:30, 3 o'clock, 3:30. Every half an hour, that timer interrupt basically triggers, and it says, go and print out what the time is right now. So while we are executing this string over here, that is running in a non-atomic way, we have an interrupt that gets called right over here in the middle of processing, printing the string out, and then it prints out the time. So instead of saying this is a line, it basically says this is 2:30, and then it would print a line after that. So this interrupt basically just came in the middle and printed out stuff like that, right? So then you can say, well, let's mask interrupts over here and just print out this, and then as we have, this is a line, it can go ahead and print out that, but then we are masking interrupts, right? So that means when an interrupt service routine happens, if we register that interrupt service routine, interrupt occurring, then we can go and service that after, interrupts are unmasked. But if, if we have another interrupt coming in, then we just don't detect them like that, right? So doing a global, mask of interrupts, like a global interrupt blocking, is also a bad idea here. So what can you do? So you can have you want to have some way to basically make this atomic and say that, anything that we are printing to the screen, now the screen basically is locked, right? So we are only locking any interrupt that is happening, to send to the screen, right? So that is what this output buffer over here is printing, is where the actual printing out is happening, right? So this is just saying that, look, we have to, even the printing to the screen is a shared resource, and we have to share that resource in a way that, first of all, doesn't call global interrupts to be masked. We're just masking interrupts to the screen. We're not masking all interrupts, right? So if there is a clock over here and I want to print that, so then it says, okay, well, you can't print yet. We have registered your interrupt and it's waiting. we're not servicing it yet, like that, right? So it's again, that interrupt has been registered. We haven't serviced it yet. So it's not even at the stage where the interrupt service routine is going to be called. And then the interrupt service routine will be called after this gets unmasked. So we'll look at that part in the second question that we had. So, but I'll just, so the second question we had was, how are these interrupts actually being serviced, right? And that goes back to this problem over here, where we have our microcontroller that is just running the code line by line, instruction by instruction, and then we can have many different sources for these interrupts over here, right? So timer, serial ports, and ADCs, etc., keyboards, pin interrupts, real-time interrupts, watchdog timers, whatnot, right? So and so there is this interrupt controller peripheral that is, where all these interrupts come into. And the job of that interrupt controller peripheral is first to detect that, hey, there is a trigger of an interrupt, and to say, okay, fine, we need to go and now we have actually got a signal that, an interrupt has been triggered. And second, it has to go and be able to respond to the interrupt. That means it has to go and actually determine which type of interrupt was there, and then it has to service that interrupt. And it has to basically tell the CPU, this is the type of interrupt that happened. You need to go and service this interrupt by setting the program counter to go and look in the memory map at the memory address of this type of interrupt, find in its address in its location the address of the interrupt service routine, and go and service that. So what we'll look at for the next 2-3 minutes is that when we get an interrupt over here, what is happening inside of this box over here, this interrupt controller. How is it actually accepting that an interrupt has occurred, and then how is it going and handing off to recognize what type of interrupt has happened, right? So the interrupt has occurred, and that could be from any one of these interrupting devices that we have, right? These interrupting devices are our peripherals. There could be any kind of sources of interrupts. It could be a network packet that is causing an interrupt to occur, and so on. So we have to do some signal conditioning. That just means that when an interrupt occurs, you have to just treat it as a digital signal. So, but if there is like any noise or anything, we have to run it through some set of filters. And then it basically feeds into a IRQ flip-flop, right? And this is a SR flip-flop or a set reset flip-flop. And all this is doing is just registering a 1 and saying that to the flip-flop that store a 1 in your buffer, that we have an event that has occurred. And then it forwards that 1, and it has saved that there in the buffer, and it's forwarding that 1 to this AND gate. And if global interrupts are enabled, then, and this particular interrupt is enabled, then it forwards that signal that, hey, some interrupt has happened, and now you need to go and service it. So then this interrupt controller will say, okay, I have detected that an interrupt has happened. I'm going to go and service it. And once I service that interrupt, and what does service that interrupt mean? It just means that it is recognizing, it is going to go and identify what is the party or the peripheral or the source of that interrupt. And then once it recognizes that, it goes and sets a trigger for the CPU to say, hey, CPU, once you're done with your current instruction, then go and service this interrupt. And this is the, this is the type of interrupt. So go to that address of that type of interrupt. And so that could be like, a timer overflow interrupt, for example, right? So and then it says, okay, I'll go to the timer overflow interrupt vector in the memory map and go and find the address of the timer flow overflow interrupt service routine. But then it's the interrupt controller is done. It's saying I've already informed the CPU, and we'll look at these two questions, right? How does it go and figure out that now once it knows an interrupt has happened, what type of interrupt is it? And the second question is, how does it go and tell the CPU, now go to that address, this is the type of interrupt that has happened, right? So once it basically lets the CPU know that this is the type of interrupt that has happened, then it just acknowledges, it gets an interrupt ACK from the sequence controller that says, okay, well, I got your interrupt message, and we're going to interrupt whenever we want to, but you can go ahead and capture the next interrupt that's happening. And so it just goes and basically resets this flip-flop. So anytime a new interrupt comes in, then that new interrupt will basically that trigger will be saved over here. And but now this only once the previous interrupt that has happened, that came in, has been serviced, and we are out of that interrupt service routine, then we basically go back and enable the set reset interrupt enable flip-flop over here, and then we can go and process the next interrupt. So the bottom line here is that I can service one interrupt at a time. While I'm servicing one interrupt, at the most I can just buffer the fact that another interrupt has come into the system, but I can't process that other interrupt till I'm done with basically re-enabling the interrupts again. And when do we know that an interrupt, the global interrupts can be enabled again? When do we know that? Question for you guys. Like what is the line of code where we know that global interrupts can be enabled again?
Isn't it like SEI? You're saying?
Yeah, that's SEI means, set global interrupts to be active. But who calls SEI, right? I mean, you aren't calling that in your code actively. You're calling that once in your code at the beginning to enable global interrupts. But once an interrupt has occurred and we go to the interrupt service routine, service it, then how does that interrupt service routine signal to say, okay, well, SEI again?
Maybe just when it returns?
Yeah, so when there is a close parenthesis, who is actually writing SEI again?
The hardware?
No.
Compiler?
The compiler, exactly. So in the last lecture, we looked at the prologue and the epilogue that the compiler adds after and before the actual interrupt service routine. The compiler is actually calling, enable and disable interrupts. So whenever we call the return from interrupts command, which is basically what the compiler inserts at the close parentheses at the end of your interrupt service routine, then that is when the compiler re-enables the interrupt. So when do you see this in your code, right? In the first 1/3 of the semester, you enabled like interrupts for like a timer or for input capture, output compare, PWM. And when the interrupt basically went to the interrupt service routine, and it finishes that interrupt service routine, the compiler will basically add a signal to say, okay, interrupt done, and now you can be interrupted again after that point. Right? So when you're polling, you basically get a flag and you need to explicitly clear that flag to move on. And here the compiler is basically clearing that interrupt is busy flag. And that's when we basically when we enable interrupts again, now going back to the screen here, we are again allowing this interrupt enable flip-flop to basically now say, okay, well, let's service any interrupts that are waiting for us, or be open for servicing any more interrupts. And so now we go to the next part that, okay, now I've detected that there is an interrupt over here, and I need to go and figure out what interrupt is that, right? So I need to go and be able to decode that. So we looked at two ways in the last lecture. One was with a polling based approach that is written in software over here that basically says, okay, I'm going to go on to the, I've detected that there is an interrupt happening. I'm going to go and check now and query every peripheral and say, hey, did you do it? Did you do it? Did you do it? Did you do it? And then basically I'm going to go and check their, interrupt flag over there, whether they have triggered an interrupt. And I'm going to go and check that flag. So basically the interrupt controller, and this is not just the CPU over here, the interrupt controller is going to go and check. So in this case, it is a software based approach. So here the CPU says, okay, I've got an interrupt. Now the CPU has to manually go and check and poll each of the devices to see, is your interrupt flag, is that high? Is that high? and then it's actually just checking one by one through writing the address of the interrupt flag and checking the data, whether it is 1 or 0. And so it is manually polling all of the peripherals, right? So this is not what is happening in our hardware. What is happening in our hardware is that we have a hardware-based way of saying, okay, well, automatically now the interrupt service, interrupt controller is going and reading from all the peripherals and saying, and it's just letting all the peripherals, it's querying all the peripherals in a broadcast way and saying, whoever raised their hand, tell me now. And then that peripheral will basically come and raise their hand and say, okay, I did that. And but this works only when you have one interrupt at a time, right? We can't service more than one interrupt at a time. So saying who raised your hand, and then that peripheral basically replies. And now obviously you'll have a question, hey, we have one, and then we have one more interrupt being serviced, but that one more interrupt hasn't been acknowledged yet, right? So we are just saying, okay, well, who is the interrupt? We are only servicing one interrupt at a time. So we can't service more than one. So that's why we can broadcast on the all addresses and saying to all the peripherals to say, do you have an active one? And then that peripheral will just respond. So it's basically like a query and response approach to actually decode which peripheral actually had that interrupt. And that peripheral will say, hey, I'm the ADC, I had that interrupt, and it just returns the ADC, not the ADC value, it just returns the ADC's ID and says, I'm peripheral ADC. Now, this is not an active instruction that the CPU is executing over here, right? So this is essentially an instruction like that is happening, communication that's happening between the interrupt controller to the peripherals. And when the peripherals basically respond, the CPU reads that response and says, hey, okay, so this is the interrupt that I have to go and service. And then it goes ahead and executes the interrupt service routine at that point. So that's how this, how interrupts are serviced over here. And there is a software-based approach, there is a hardware-based approach. There are other aspects of, how do you mask interrupts, interrupt priorities, and, and having nested interrupts. But any questions so far on this? Does it make sense? Kind of, sort of.
Yeah, it makes sense.
Okay. Okay, should we go on to the next question then on the Watchdog timers? Yeah. Okay, so let's look at Watchdog timers next. And then if you have other questions, then let me know. So why do we need a Watchdog interrupt, right? So let's go through this example over here. This pretty glaring example. So back in 1994, right, long time ago, there was this deep space probe called the Clementine, and that was basically launched to monitor the moon and some asteroid near the moon, right? And so this was supposed to be like many month-long kind of operation, and usually these kind of probe spacecraft, they have some fuel on board. They have like these solar panels that you see, but they also have some limited amount of fuel on board. And mostly that fuel is just used for thrusters to just realign itself, periodically, right? But these thrusters will just be turned on maybe like for, few hundred milliseconds, just to cause like a 1-2 second realignment like that, right? So if you guys have, I've been rewatching a lot of these James Bond movies and regretting it, but because they're so lame now. But like if you watch a movie like GoldenEye, right? So you can see the thrusters are basically causing, the satellite to realign and reposition itself. Like how does it know? Suppose how does it actually pinpoint to find your home, right? That is a little bit off its axis of, off its orbit like that, right? So if it wants to change its orbit. So it's using these thrusters only to a very limited extent for just a few hundred milliseconds. And but what happened once was that there was a software exception, and that caused the thruster to fire for a full 11 minutes. And basically 11 minutes for the thrusters to be on is like a long time, right? And it basically exhausted all the fuel, and it also caused the space probe to just keep spinning at like 81 RPM. And that was the end of the mission, right? So here the problem is that, if you and me saw this space probe, firing its thrusters for more than a minute, we'd be like, hey, something is wrong. And then we would go and hit the abort button, and we would just tell the thruster, whatever you're doing, just reboot now and get back to the main program, realign after that, right? But right now it's just basically spun out of orbit, and it's too late. Like, we've lost that kind of thing, right? Um, so what we would, if you and me were watching the space probe and we had direct control over it, we would be like, hey, this is something wrong. Let's just stop it, because it's just been firing the thrusters for too long. But now you and me can't like observe this space probe over here and always be monitoring it. So you have to have some kind of a system that says, well, if the program is stuck or some actuator is stuck for too long, and we are detecting that the actuator is stuck for too long, then we need to just cause the program to time out and say, okay, guys, time out. We need to abort whatever you're doing. Something is wrong in the system. We can either diagnose what is wrong, or we can just reboot the system. And it depends on what kind of recourse you want to have when you realize something is wrong. But the way to realize something is wrong is to have a timeout, right? And the timeout basically just says, okay, if something is running or it's stuck for too long, then we need to basically just do something about it, right? So, but we need a timer to detect that something was wrong for so long. So one way to do that is to have this system called a watchdog timer. And so essentially it's the analogy here is that this watchdog is watching a system, and before, and you're setting this timer, and before the timer times out, you want to feed the dog. And if you don't feed the dog and update the timer again, reset the timer to start again, and the timer actually times out, then it'll go and reset the system. So the point is that if you don't feed the dog, it'll come and bite you, right? And if you feed the dog, then the dog will not bite you for another, let's say, 3 hours. Then you need to feed the dog again in 3 hours, and then the dog will not bite you, or it'll not come and lick you and nag you and jump on you and all of that, which is nice from time to time, but you need to feed the dog like that, right? So I don't know, how many of you guys have a dog at home? Are you guys taking care of the dogs, or your parents are? So the point here is that any kind of pet you have, you got to feed it from time to time, right? So that's the analogy here, but we'll leave that analogy to that extent, right? So essentially this timer is there. Before it times out, we need to basically go and restart the timer. If we don't restart the timer because we are stuck in the processor in some kind of place in the code, and then this timer times out, then it comes and restarts the processor over here. And this is exactly what happened in the Mars Pathfinder in the late 90s, that they basically succeeded in getting a Mars rover for the first time on Mars, and it was driving along, and after a few minutes the rover essentially just stopped, and it was on Mars surface, all systems were functional, but then it just started rebooting, because it basically was trying to do some database upload. And then the motor controllers were like, hey, we need to rotate, but the rotate command was sent, but the encoder for the wheels did not update the actual position. So then it just kept rebooting, because the whole processor was stuck with backing up the images that it had just taken. And so now they spent like hundreds of millions to send this probe to Mars, and it's just sitting there on the surface. All systems are go, except that it is just rebooting. And so that's another problem that is related to like priority inversion with the real-time operating system. We won't cover that, but essentially that's what was happening there, was that the watchdog timer was timing out. It was just resetting the processor again and again, but then the humans had to come in and then reprogram the system remotely, right? And you can imagine how hard that is, because each key press, who knows how long it takes to send like a signal from Earth to Mars. I mean to Mars. Any aero astro geeks over here?
Like 7 minutes, right?
A long time, right? On the order of several minutes. So imagine you are trying to debug the system. I know some people are complaining, hey, my virtual machine has slowed down a lot because I gave it too little RAM. But imagine that every keystroke you press takes 7 minutes to come up. And if you make a mistake, go to delete, 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 and then put another, or you're compiling some code, sending it over there, takes 7 minutes, to just take for the first byte to reach, and then you're like, oh, that was a mistake, and then you have to keep doing that again, right? So that's so yeah, don't complain about your VM slowing down. I mean, complain about it, but also increase the RAM that you give the VM. So so that's the problem with the Mars Pathfinder. So, but basically this Watchdog timer is, we want to prevent it from resetting us, right? So so ideally you would actually have an external, like if this is your computer, you would have an external hardware that is the Watchdog timer, because you don't want it to even be on the same system. And all it is doing is saying that, hey, if you don't give me an update every time, it's kind of like your parents, right? Say you go, like if you weren't quarantined at home, and you would just go home and then you would go and party with your high school friends, and then your parents would be like, okay, I know you're all grown up and everything, but just check in at midnight, check in at 1 o'clock, and just send us a message that, I'm okay. And then if you don't do that, and you don't like send a message till like 3 a.m., then your parents will freak out, and that'll unleash the watchdog in your parents, right? So so similarly, you want to basically keep this watchdog timer updated, that all systems are okay, reset the watchdog timer. So there are internal watchdog timers and there are external watchdog timers. So let's look at how this watchdog timer would work, right? So this is an external watchdog timer over here. This is basically a chip that only does that, right? It is just a watchdog timing chip, and you basically send it a watchdog timer input, and it goes and updates the watchdog timer. And if it basically times out, and you can program this to say, okay, timeout after like so many milliseconds, hundreds of milliseconds, it will go and reset your chip if it times out. So its main job is to just sit next to the main processor, and the main processor is just this really small timer IC, and all it does is just wait to reset your main processor in case the main processor gets stuck, right? So it's kind of like, I don't know how many of y'all have watched this movie Inception. No, okay. If you haven't watched it, you should watch it. It's really long and it's kind of slow, but it's an awesome movie. Okay, so but in Inception, you can think of it as like, so say you're a human and you're going on a space mission, but you're alone, right? And if you go to sleep now on the space mission and you miss the main sort of landing point, for example, you set an alarm and you keep saying, and the alarm keeps waking you up, say every 6 hours, to say, hey, check outside, you shouldn't miss what you're waiting for. So this is kind of an alarm system. It's just that you don't want this alarm system to ever trigger, because then it'll actually reset here. You only want it to trigger when the processor is stuck. So let's look at some ways of doing it in your own code, right? So if you have some monolithic code like this, that is reading sensors, controlling a motor, updating some display, then at the end of that code, you would say, okay, system check, all systems are go. And then it just goes and tells the watchdog, look, we are okay. And then the watchdog timer basically gets restarted. And that's just like a simple timer, right? It's just that in this case, we have a dedicated timer that we are assigning to as a watchdog timer. And if the watchdog timer basically, has timed out by that time, then you basically flash LEDs and report an error. So while this looks great, what's the problem over here?
The counter of the watchdog timer won't update if the code gets stuck.
Yeah, so if the code got stuck here, we never come to this point. And, we have like our code to report an error. But, if I never got to that code, then that's too bad, I mean, you put in all of this, watchdog stuff over here, but you're never going to execute that line of code because you got stuck somewhere with the display status or with reading sensors for that, right? So what is the other problem with this kind of system? Say we don't get stuck in the code, but what other problem could happen over here? Don't worry, I won't time out. I'm just waiting for y'all to give me an answer. There's no watchdog with me. Everybody's thinking someone else will answer. So let me give a hint that the code actually ran correctly, but the watchdog reported a fail.
Is it if the system check goes bad?
Let's say the system check is fine. We don't get stuck in any line of code. It's just that the code ran correctly, but it still reported a fail. When would that happen? So you're right, you're close to that, right? So the system check, obviously we are reporting a fail, so system check said it's not okay. But what is the system check doing? The system check is basically looking at the watchdog timer and seeing did it time out or not. And so the system check detected that the watchdog timer timed out. So what is the situation where the code ran correctly, but the watchdog timer timed out?
Could it be the code runs too long and it runs longer than the watchdog timer?
Yeah. So sometimes your code could just run on a fast path, right? It would just be like, if you have like if else, or for loops, and it just goes to the for loop and then it exits for the for loop in the first iteration, then the code ran really fast. It's not like the code runs the same amount every time. It depends on the conditionals in your code, right? So suppose you have an if, and you go through the if, and you have 10 ifs, and you just go through the ifs, all the ifs, and they all are very quick. Then you basically can go and check, okay, system check, watchdog timer hasn't timed out, we're okay. But if you go through the else's, for example, and the else's take a long time because they have to actually do a lot of work, then your code to go from, since it's monolithic code, to go from the first statement of watchdog state advance to the system check if statement over there, that's going to take a long time, and your watchdog timer would have timed out by that time. So you have to, then you have to say, okay, well, sometimes this happens when you're initializing a system. You're just booting up a system, and when you're booting it up, it's going and setting up all the launch tables, it's setting up all the configurations, and it takes a long time to actually get started with the first task when it boots up. So that first time also is when the system could fail right in the beginning, because your code just took the longer path to execute, that took a longer time to execute, and by the time it reached the system check, it was your watchdog timer was set to the best case or the average case. It wasn't set to the worst case of timing over here. So you want to set your watchdog timer not to be, you have to measure what's the worst case timing your code could take, and say, okay, my worst case timing, this code could take 120 microseconds. So I want to set the watchdog timer to be at least something more than that, like say 150 microseconds. If it takes more than that time, then I know I'm stuck somewhere, right? So I just want to discriminate between being stuck in my code versus, going through the slowest path of my code like that. So that's one thing over there, right? So what we can do then is, suppose we have multi-threaded implementation, right? So that means I have a monitoring task, and I need to basically check are all the different tasks, task 0, task 1, task 2, are they all okay? And each of them is like a task, right, running in the operating system. When task 0 runs to its loop and finishes, just before it finishes, it goes and sets a flag and says, hey, flag index 0, I'm alive. And same thing task 1 and task 2 do. And all this monitoring task does is that periodically it goes and checks in and says, hey, are all flags alive? If all flags are alive, kick the dog. By kicking the dog, or a nicer way is feed the dog. It's basically just saying reset the Watchdog timer. If all systems are not alive, then record the failure, record the flag index, and then basically call the Watchdog. Now the Watchdog can do what? The Watchdog can obviously reset the system. It can send an interrupt and say, hey, Watchdog has a problem over here. It can do things that are non-fatal, right? Not just doing a hard reboot of the system. You can actually program the Watchdog to actually have a response like that, right? But here it's basically this monitoring task is making sure that none of these tasks are hung up for any reason like that, right? So the OS will keep switching between the tasks, but these tasks could just get hung up and then they would just be locked where they are. And that's exactly what happens, like, you know, when you have a program that crashes and you need to go and kill the program, right? In Linux or Unix, you would use kill-9 and then the program ID number, the process ID number. In Windows, for example, you would just call the, you know, activity monitor and then kill that task. And same thing in Microsoft, you would call the task manager in Microsoft operating system, and you would kill that task, right? Basically, that task was stuck somewhere, and then, you know, it's sending you some signal that, hey, this task is stuck. You need to. Usually, the signal is that your CPU fan starts running really fast, and your CPU starts getting heated up, and your battery starts draining out because that task is just looping over there for some reason. Now, we can't see that code in that task, but we can kill the task and restart it, right? So this is kind of like what you would do for a multi-threaded implementation. But what I want you to learn is really very simple, is that in your microcontroller and in every microprocessor and every microcontroller, you would have what is called a Watchdog timer built in usually. And this timer just allows you to take, like, you know, it has its own oscillator, and you can see this oscillator here is just running at 128 kilohertz, not 16 megahertz. So the oscillator is also running at a very slow rate, and it has its own basically clock for the Watchdog timer that is a much slower clock. And you can divide this clock heavily by, say, 1024, right? And so this is basically just a simple timing circuit over here that just says that, okay, well, this is the prescaler and this is the timeout time over here. And if I do timeout, then based on how I configure this Watchdog timer, I can reset the microcontroller with this signal here, or I can interrupt the microcontroller with this signal here. Let's look at how we would actually program this Watchdog timer, right? So we have one Watchdog timer control register over here. And so we have the prescaler for that. Here we can say, if I divide this already slow 128 kilohertz signal, timing signal by 1024, I get 8 seconds. So that's, so you can see I'm already in milliseconds and I can go up to 8 seconds. And so I say, well, if the system is stuck for 8 seconds, then, you know, reboot the processor or interrupt the processor. I can say which mode I want, right? So I can I enable the interrupt over here, Watchdog interrupt enable, and I have an interrupt flag over here. And then I select the action over here for when the overflow happens. And the action essentially is with this, right? It's just saying I can either reset the system or I can interrupt the system like that, right? So, or I can just stop the system like that, right? So, and I just, so it's, but the option over here is that I just can interrupt or reset the system. And so you would always, so since we have a slow clock, we would normally want to take, you know, the maximum time that is possible, like that's about 8 seconds, and keep it at that. So it's a very liberal reset time that just says, oh, look, if I have my node and I have deployed it all over Philadelphia in some smart cities, IoT kind of deployment, and some node basically gets stuck for some reason because there's a bug in our code, then, and I got into that freak a state of where that bug is stopping my code now, that node would just wait for 8 seconds and it wouldn't have updated the Watchdog timer, and then it would just restart over there. So here is an example of code of how to do very little but efficiently, right? So we basically are telling the Watchdog, like, we don't want this Watchdog to do anything really, but if it's not reset periodically, then it's going to like either reset the microcontroller or toggle a LED pin and say, okay, look, here's a problem, right? So toggle, so in this case, we are just using this to have like a security light, right? Like how you have in cars, you have a security light that's like every few seconds or 1.5 seconds. So that this is just one way we're just using it as a timer, like that, right? So we are not counting overflows. We're not doing any, storing timer values. All we are doing is just setting up, the watchdog, enable the watchdog, set the prescaler to be 8 seconds. And then we basically output, to this DDRB to the LED pin. And we just run that basically, for forever, right? Because the watchdog timer is just going to keep calling the interrupt, and it's just going to toggle the LED. So the LED is going to be on. In this case, it's kind of a little silly. The LED is going to be on for 8 seconds, and then it's going to be off for 8 seconds, right? So you don't want exactly that, but this is just saying, okay, with a simple toggle, I can have the LED on for, and I can just have this toggle, right? All we are doing in this case is just setting the watchdog time, using the watchdog timer as a generic kind of timer. But what I would want to do, like, like say with your phone, right? If you just leave your phone, you use your phone and then you keep it on the table, after about say 15 seconds, the screen dims. And then after about 30 seconds or 1 minute, the screen basically goes off. And then the phone also goes into a lower power mode. It goes into a standby mode. So you can implement that with a watchdog timer too. You can just say, okay, get into low power mode and sleep, either power down for 8 seconds with the ADC and the other kind of peripherals that are, disabled. And so then it's kind of saying, okay, go take power naps, right? So basically shut off for 8 seconds, then wake up. And so it's just saying, okay, power off for 8 seconds over here. And then we would use the wake up by waking up with a watchdog timer, right? So essentially we are powering down the ADC and any of the other kind of peripherals that we are actively using. And so it's not sensing stuff, but then it's waking up. So your phone is doing exactly this, but it's not shutting off for 8 seconds. It's just taking micro naps. And only once, I pick up my phone and then once I shake it a little bit, then that's going to trigger some interrupts. But essentially, so this is one way to trigger the interrupt. The other way, the phone is actually waking up periodically. It's checking the cell phone signal, it's checking the Wi-Fi signal, going back to sleep. And that's saving a lot of time, right? The whole point is the phone is not doing much at that point, and it has to do nothing efficiently. So that's just going over watchdog timers, that you can use it to, prevent the system from getting stuck. You can use it as a simple timer, and then you can use it to also just take power naps in this case, where we're just calling this function, low power, and it's and it's basically letting it go to sleep and turning off peripherals, and then we can do something else, and then we wake up with an external interrupt. So the watchdog timer will actually wake us up rather than reset the system like that, right? So, and most IoT systems have to have a really good low power operation mode, because that's how they're going to be able to last for, multiple hours or days or years like that. So so that has taken us so far, through our questions. We have 10 more minutes. And if you guys have any other questions, why don't you ask away? Or if I haven't covered anything and you want me to cover it in more detail, ask away. Okay, why don't we only have 8 people on here, so why don't we just go through everyone? So Will, Peter, Matt, any questions?
Not currently. I think this all makes a lot of
Okay.
sense so far.
Okay, Aaron, Asaf, any questions?
I have no more. You answered them.
Okay, Zia, okay, any questions? All good?
I guess one question.
Yeah.
So could you maybe go to the one like interrupt request slide? Do you remember what I'm talking about? Like we had the request flip-flop,
Yeah, in the
that
internet
diagram.
controller.
Yeah. So when we had that diagram, like we could only have one request at a time, right? Like one backlog of one request. Beyond that, it's just stuck. It's
Yeah. We are basically just we haven't interpreted what that interrupt is, but we can just buffer that one more interrupt is waiting.
So then, like, what happens if you want to buffer another interrupt? It just can't.
We can't do that in this system. In another system, you would actually have, instead of just having a flip-flop here, you would actually have a queue, right? You would have a multiple buffers over there, and you could say, okay, well, this buffer is occupied. You can try the next. You can try the next, and that's actually like if we go back to like how interrupts are in Intel and ARM processors, they definitely can have multiple interrupts in their system over there, right? So those and all of them, all major processors can allow nesting of interrupts, can have multiple interrupts, can have masking of interrupts. And I'm just trying to find one slide that shows, I think, Intel or ARM's interrupts. So the other thing is that, I just want to show you some other aspect, like, okay, over here. So I think, so the other thing that, there are some hacks also that happen, that when you have like, interrupts. So what happens when you get an interrupt, you basically push everything that's running on the CPU onto the stack, then you service the interrupt and then pull everything back on the stack, right? So now if you have like back-to-back interrupts, suppose I have two interrupts back to back, then does it make sense for me to do this, right? Do I push everything on the stack, service the interrupt, pop everything off the stack, then again push everything on the stack, then service interrupt 2, then pop? So what they did with the ARM Cortex M3, which is like in your embed microcontroller, they did this interrupt, chaining over here, cycle chaining. It's called the tail chaining. They just pushed everything that is running from the main program, service the interrupt, then they said, hey, wait a minute, we have another interrupt waiting. Why should we pop everything and push everything again? We're just going to detect what that other interrupt is and service the next interrupt and then pop everything off and then continue after that. And they found that they could actually save 65% of this overhead by not doing this, redundant pop push over here. And so that saved 16 cycles plus 26 cycles. But it took them like 6 cycles to actually run like some intermediate firmware that was just saying, okay, well, we have another interrupt waiting, so we don't have to push things back again. So this is a way of lowering the latency when you have back-to-back interrupts. Now your question is regarding like, can I have, I want to have more than one interrupt waiting, and most microcontrollers will allow you to do that. In fact, most so this is another, what they would also do is they would have something called what is called a FIQ, which is a fast interrupt service. And so that just means that they say, look, you don't have to save all the registers onto the stack. What you can use is we just have some dedicated registers that you can save your data, and we have a copy of, we have extra registers for the, okay, looks like I think I removed those slides of using the FIQ, but basically they have extra registers, so you don't have to push stuff onto the stack, and you can go and service that very quickly. But that's just another way of, lowering the latency for interrupts. It's not necessarily, it's so to have multiple interrupts here, all we are doing is we are actually extending this flip-flop to actually be like a multi-stage buffer, so we can actually buffer more interrupts that are waiting in the queue. And all operating systems, they actually service this buffer. They have a way to service this buffer very efficiently, because they have a queue, and then the operating system also says, okay, well, we have registered a queue of interrupts that is waiting for us to service. and then they go ahead and service that queue of interrupts at that point, right? So so this is also like related to what the operating system can read, and the operating system is informed that, hey, add one more to your queue, add one more to your queue. And so there's like there's a pipeline essentially for interrupts to be serviced in that case. But for our course, you don't have to worry about that. If you do like a real operating systems course, you would have to like actually implement some of that, right? You would have to implement like a interrupt service queue, and then you would really understand how that happens. And if you're really interested, then ask a question on Piazza regarding like how does Linux do this, right? And then Linux has like a lot of documentation on how interrupts are serviced, what is the best way to service interrupts, what is the best way to use these tasklets or soft IR queues or interrupt service queues efficiently, and how does the kernel actually keep track of a queue of interrupts and then service them in a prioritized order. So it's actually pretty complex and complicated under the hood, and each of the operating systems handles these in different ways. And that's how one operating system competes with another and says, look, we have much better latency of doing this. And that's why most like industrial kind of deployments of operating systems, like in data centers, they don't use like your Mac OS or your Linux or your Windows as you use on your laptop. They have specialized versions of that are really stripped down and that are highly optimized to minimize this latency for handling like multiple interrupts. You can think about it like this, right? You have a web server that is getting like 1,000 requests per second, and suddenly it spikes to 10,000 requests per second because Corona hit, and now everybody is like checking the news like 20 times a day. So the web servers are basically getting hit so badly right now that they have to be able to service all these requests. So what do they have to do? They have to say, well, one front end unit can handle 10,000 requests per second. Then we need to add another one, but there has to be some load balancer. And this is like at a system level of how requests are coming in, because they're all getting clogged by the number of interrupts, and the queue is becoming too long and the latency becomes too long. If latency becomes too long, then the service requests basically start to drop off at that point. So managing latency is like, is a job for so many, engineers within a lot of these data-driven companies out there. Okay, a little bit long-winded answer, but hopefully it gets the point across there.
Thanks.
Any other questions?
So when it goes into a low power mode, you said it could have an external interrupt, take it out of that low power mode.
Yeah.
That work specifically, what checks would you have to do? Like, would you keep on just running the interrupt handlers in low power mode and you turn off the other stuff? Or
yeah, so say like the ADC. The ADC is actually quite a power hungry system, right? Because the ADC has to run the whole like successive approximation circuitry. It has to run its own sort of clock internally, and it has a lot of transistors to power on. So essentially, when we are running a system in low power mode, what we are doing is we are just going and turning off different peripherals. And generally in circuit design, or chip design, this is a very like old technique from when chips actually started getting designed. It's just called a clock gating technique. And clock gating is just saying that I'm just going to not give you the clock. If I don't give you the clock, you just collapse, just sleep. You go to sleep instantly, right? So so what we are doing here is that we have an external interrupt. So this is saying that we have this kind of a maxim controller that is external to our system, and that external interrupt is not resetting us. It's just saying, it's just giving you a slap and saying, hey, wake up, dude. And then you're like, oh yeah, I need to go and check my ADC. And then you go back to sleep again, and then again comes and gives you a slap and wakes you up like that, right? It's not so violent, but it's just basically telling you every 8 seconds, wake up like that, right? So yeah, so another little cheesy but interesting movie is called, I think it's called In Time. I don't know if you guys have watched that one, where everybody basically if you work for a day, you get maybe about a day and a half of time to live. So you have to go back to work. It's like going back to the Amazon, center, and then so you're getting paid in terms of time to live, like that, right? And so that's an interesting way of looking at life also, where you can have a timeout and you would die if you run out of time. So very rich people have like years and years of time, and that's all on their wrist, like that, right? So, so they are very rich because they can stay young for a longer time. But then poorer people, they just have like time to last, like say till the next day. So they have to go to work, and when they punch their time card, they basically say, okay, you worked for 8 hours, you get 16 hours of time to live. And so it's like this corona, right? This corona has shut down so many restaurants, and a lot of people who only had savings for a short amount of time, and they are going to start suffering, or they already are suffering really, like day laborers, like that, right? Versus many other people, they have savings, like that, right? So but here, that's just money savings is different from whether how much time you have left to live. And so that movie is called In Time. That's another way of looking at Watchdog timers, where people actually die if they run out of time. So, okay, a little bit off track, but yeah, essentially this is an external interrupt that is saying, okay, well, you can keep powering off your system. I'll give you another example. So back in the early 90s, when cell phones started coming out, the cell phones, they just had like these gigantic batteries, because battery technology wasn't as good as it's today. And they could only last for a few hours, right, of talk time, maybe like 45 minutes talk time, and the cell phone is dead, like that, right? So so then Motorola came out with a new design, and they designed the cell towers and they designed the phones. And what they found out was that even though the cell phone isn't being actively used, the problem is that it's still draining the battery really fast. And so what they found out was that every time the cell tower keeps talking to the phone and saying, hey, hello, are you here, are you here, are you here? So every 100 milliseconds, or every, like in that time it was, I think every 10 milliseconds, it's talking to every phone and it's saying, are you here, are you here? And they're basically chatting a lot, but they're not really having a call. It's just the cell tower needs to know where every phone is at any time. Because if you get a call or you get a message, it needs to know, it needs to send that to your phone, it needs to send that to that particular cell tower. Like, I'm in West Philly now, it needs to send it to the West Philly AT&T cell tower. So AT&T knows that I'm right now in West Philly because my phone keeps pinging them, right? So so what Motorola did was they were like saying, okay, look, these phones are doing nothing, but they're doing nothing but they're too chatty. So they just reduced the time, from 10 milliseconds to every 100 milliseconds for the phone to say, hello, I'm here, hello, I'm here. And that basically increased the lifetime of the phone, to be more than 24 hours. And then to basically, that's how the earlier phones, I don't know if you guys ever had those Nokia kind of, what are they called? The candy bar phones. They could last like for 5 days, 7 days without charging, right? Unlike our smartphones today, because they just are pinging and polling the cell tower so infrequently. So that was just one way where they just turned down the rate of getting updates. And that's one way to lower the power. In this case, we're just basically clock gating and turning off peripherals, but waking up again, checking the peripherals. So what this is doing is very similar to what this phone is doing now. See, this phone now turned on. And then if I just keep it like this, it'll turn off after some time. But if I shake it, it should come on, right? So right now it's not activating. And then if I tap it, it's detecting an interrupt. Here, this interrupt is from my tapping, but otherwise what the phone is also doing is that every few hundreds of milliseconds, it's waking up, checking everything and going back to sleep. But the point is that 99% of the time, it's really not doing anything. And by not doing anything, it should basically be sleeping 99% of the time, but it has to respond to any new signal that comes in, with a minimum latency. If it goes to sleep for 500 milliseconds, then it's going to take 500 milliseconds to respond for the first time. We'll see an example of this with the networking protocols in the week after, for wireless networking protocols, of how, the more energy you want to save, the less responsive the system, and how do you try to balance that with that, right? So Okay, so any other questions you guys have? All okay? Ready for the quiz? How far are you guys with your worksheets and the lab?
It could be better.
Yeah,
Worksheet, still finishing up the lab.
yeah, good. You still have some time, right? So, okay, all right. Ask us questions on Piazza and okay, good. So and if you have any and we'll also sync back up on Thursday for serial communication. Yeah, if you have questions regarding pass fail, then I'm just going to stick around for some time here, and whoever wants to talk about pass fail stuff, you can stick around, and then or I can talk to you all one-on-one privately. Okay, all right, that brings our lecture to an end, and I will stop the recording also over here. And so if you have any last questions, let me know.
See ya.